In this next video, we are going to talk about some examples of electric fields from different configurations of charges. All right, now, I introduced in the last video Coulomb's law, and we talked about how Coulomb's law can be applied to a discrete set of charges, how it can be applied to a line of distributed charge, or to a surface of distributed charge, or to a volume of distributed charge. And in principle, if I give you any configuration of charges, you can plug in and solve an integral and calculate it. But that's not really the purpose of this course. I'm not interested in having you analytically solve triple integrals and remember some of your integration rules. I really want you to understand the concepts of how electric fields relate to charges. Because in real life, as I'm going to talk about a number of times, problems like this are solved numerically. They're not solved analytically. In fact, it's a very small number of problems that you can solve analytically, and they tend to be all found in physics textbooks, and you probably have already seen several of them. So we're going to look at this from a different perspective. It is very useful to look at a charge configuration and quickly have some sense of roughly where the field lines are going just from intuition. So let's look at a few cases. I'm going to write down what the answer is if you were to do the integral, but it's not my expectation for you to specifically know how to calculate these integrals. And so we already did a point charge, and that's probably the easiest one. And let's say we got a point charge with positive Q, in which case the field lines are simply going to be streaming away from that point charge in all directions. And for that, the electric field will simply be Q times an r hat vector that points away from the charge itself, divided by 4 pi times epsilon naught times this r vector length squared, right? Where r is any particular location where we want to know what the electric field is, right? So this is R, right? And this is where we want to know what the electric field is. We calculate it by placing R in here, along with the value of Q at the source. All right, so that's a point charge, and that's the simplest. That's just Coulomb's law directly applied. And this makes sense from a water analogy perspective, that water is simply going to flow away from that hose that's dumping it in at a constant rate. All right, let's take a look at an electric dipole. So in an electric dipole, we have one positive charge. Sorry about that. We have one positive charge with magnitude positive Q, and we've got a negative charge that has magnitude negative Q. And I'm going to define this vector D as being a vector that points from the negative Q to the positive Q. That's going to be defined by the vector D. All right, if we do that, let's try to envision what would happen. We'd expect very close to the source, we're going to have field lines that are streaming away from the positive, and they're streaming toward the negative source. So these field lines are converging into the negative source. These field lines are going to be streaming away from the positive source. And these are simply going to connect with these little loops like that. And these loops will sort of get bigger and bigger. So this is the field lines that we expect from a configuration like this. And these outer field lines are just going to kind of go off into the distance. All right, so here is where these field lines are pointed. Always from the positive charge to the negative charge, or they're away from the positive charge and toward the negative charge. Right, and this is called a point dipole. All right, I'll give you the answer of what that electric field is if the length of R is much less than the length of D, which is to say you're much further away from the dipole as the dipole is separated. Then the electric field can be approximated as minus Q times this vector D divided by 4 pi epsilon naught times the length of R cubed. Sorry, times the length of R squared. Right, so this is the electric field for a point dipole. Right, where again, D is a vector that points from charge 1 to charge 2. The presumption in an electric dipole is that the positive and negative charges have the same magnitude. They're just opposite in sign. All right. The rest of these, I'm just going to draw the field lines. I'm not going to draw the equations. The full equations are in the notes. But let me just draw them out, and then let's define what the field lines will be. So this is called a quadrupole. Quadrupole. And in a quadrupole, we have a value of negative Q as a charge over here. We have a negative Q that's over there. And in between them is a charge of plus 2Q. You can think of this as two dipoles, except one of them moves this way. And so the dipoles overlap. And so in the middle, you get double the charge. And on the outer ends, you get sort of a single charge. So let's try to imagine, again, you've got twice the amount of water that's being spewed out from this positive charge. And about half as much of that is sucked into each of the negative charges that are around it. So we can certainly expect to get this sort of a structure where field lines are flowing from the positive charge to the negative charge. And that's going to be the case in both directions, right? We're also going to have charges that are flowing to this lower negative charge, like this. And then we're going to have field lines that kind of go way off and maybe take a long time to loop around. Right? These field lines that I'm drawing, I'm not showing a full circle, but if I did, this would kind of go way off, loop around, and would come back around on the other side and land over here. Right? So these are all circular field lines that I'm drawing. Right? And this is called a quadrupole. The equation for this is in the notes, but this again has an analytical expression for what the electric field is if you are reasonably far away from that dipole, much further than the separation distance between these charges. All right. So next one to cover is an infinite line of charges. All right, so this is a line that goes off infinitely far, and along it is a distribution of charges. And in this case, we're going to assume that that distribution is constant along the line. All right, so rho L is constant. This is a infinite line charge. And for that, we're going to have electric field lines that are flowing straight out in both directions from this positive charge. If there were negative charges, you have the field lines going in, but I've drawn it positive. Right, so it's always going radial away. It's not looping around because it essentially never has a chance to. This line is infinitely long, and so there's nowhere where it can wrap around and come back. So these lines proceed off into the distance and basically never bend. If we do that, then the electric field works out to be rho L over 2 pi times the length of the vector r times epsilon naught. All right, so this is the electric field from an infinite line of charges. Notice that what was an r squared has now become a 1 over r. And the way to think about it is, since this line is infinitely long, we've kind of taken away one of the two dimensions by which those lines are spreading out. Right? They only sort of spread out in one direction as a function of angle. They're not spreading out in the z direction or up and down in this diagram. Right? So this is an infinite line charge. Let me also contrast this to the finite line charge. In the finite line charge, the line ends right here. And you've got this length right here. Let's say you've got this line segment A, and you've got this line segment B. And we're talking about the electric field here at this point. So this is our location where we want to calculate the electric field. That's our vector r, right? Pointed to here. Draw that better, right? Here's r. So here's our vector r. If you work out Coulomb's law and apply an integral to this, you get that E equals rho L over 4 pi epsilon naught times Z times B divided by square root of Z squared plus B squared plus A divided by Z squared plus A squared square root, and all that is in the r hat direction. Right? R hat is going to be a unit vector pointed away from the line. All right, so this will be the finite point charge, or finite line of charges. Will fit this equation, and you can figure out what this is for kind of any location within the interior of the line segment and put off to the side. All right, and I assure you, by the way, as an exercise, you could apply this equation and make A and B both become really, really, really big. And as you do that, this equation will collapse and will become the same as the infinite line charge. You can verify that yourself if you like, but it is the same equation. All right, I want to run through these last few a little quicker. There is a ring of charge right here, and oftentimes it's useful to consider a point that is perpendicular to the surface of the ring itself. But this ring has uniform charge distributed along it, so positive charges distributed around like that in a circle, in which case the electric field equals A times Z divided by 2 pi epsilon naught times Z squared plus A squared to the 3 halves. And this will be in the r hat direction. Notice that r is specifically in the perpendicular direction from the surface. So this angle right here is 90 degrees. This diameter of this circle is 2a, so a is the radius of the circle. And this vector right here is the z direction. So z is the length in that axial direction that's through the ring. All right. There's also the disk of charge. That's a solid disk that is filled with positive charge as opposed to just a ring around the outside. And the electric field for that is E equals rho S divided by 2 epsilon naught times 1 minus Z over square root of Z squared plus A squared. And this again is for a point that is located perpendicular to the surface of this disk, right? Or perpendicular to the center of this disk. So draw a line straight up. This vector right here is R. And the direction of E will be in the r hat direction. So again, pointed away from positive charges. All right, the last one is going to be the infinite plane of charge. This one's going to be kind of important later on. So it's probably worth memorizing this one. Right, this is an infinite plane. I'm only drawing a piece of the plane, but it extends in all directions. So I'm going to draw the arrows there because it's an infinite plane charge. You can figure that out if you take the disk of charge, or the disk of charge, and simply set the radius to be infinite, right? And when you do that, this whole second term right here is going to drop out, and so the electric field will simply be rho S times r hat over 2 epsilon naught. Now this one is really interesting because it's a constant, right? This does not change depending on your location. Rho s is taken to be a constant number. 2 epsilon naughts is a constant. And so no matter where you are, you can move really far away from the disk, or you can move really close to the disk. You get the same electric field. And that is mind-boggling at first until you consider the dynamics of what's going on. So let's think about the case where we have a segment of wire, and there's charge distributed along that wire. And then you start zooming away from it. The wire gets further and further and further away, off into the distance. It's a mile away, and then it's 10 miles away. What you see is that wire starts to get smaller and smaller from your perspective. And eventually it becomes this little speck way off in the distance that you can no longer really see. So a finite length of wire eventually collapses to becoming a single point. And so you can basically approximate it as if it were a single point. But if the line were infinitely long, then no matter how far away you go, you never see the end of that line. It never collapses down because it's just way too far away. Or it's infinitely far in both directions. The same effect is sort of going to be the case for a plane. If I have an infinite plane extending in both directions, as I rise up over the top of it, there's no point where it starts to collapse into being a single point. It's always going to extend out infinitely far, and I'll never see that no matter how far away I go. That's one way to understand why the infinite plane charge just has a constant electric field. The only difference is that the electric field is pointed upwards on one side of the plane, but is pointed downwards on the other side of the plane, because this r hat vector flips signs depending on whether you're above or below this plane. That's the only change that that can result. Other than that, the electric field is constant everywhere. And this is going to be important later on as we consider a couple other more advanced concepts. All right. So I'll stop here. In the notes, there is a little more information about how you actually calculate this analytically for a given example. The number of cases for which you can actually apply Coulomb's law and figure out what the electric field is are very small. You can probably count them with your two hands. The ones that have these neat analytical tricks that you can just apply directly. So in general, Coulomb's law works always, right? Or at least for all the static situation that we're considering. But in practice, you end up having to integrate an equation. And in most real world scenarios, you can't simply integrate it because you have some arbitrary variation, or you have some kind of a weird function that doesn't have a straightforward integral to it. The ones I showed you are kind of idealized. You can find these in textbooks, and there's kind of a known answer. And that's helpful as far as building intuition goes. But exact answers in reality are pretty much always determined numerically. And what that means, when I talk about numerically, is that you're basically going to take space up and you're going to divide it up into small little pieces. Each piece you can treat as being like a discrete charge, and you can sum all those up numerically. 5 plus 7 plus 12, and you get an answer. And so what we're trying to do here is build up the understanding so that you can solve those problems numerically, but also understand the intuition. So if I shove a different configuration of charges in front of you, you can kind of figure out where the field lines are anyways, even if you don't have an exact number to how intense the electric field is. However, the steps to solve the electric field are important. And so that is in the notes. There's basically like a simple set of steps that you would apply. And this works if you're doing this analytically, but it also would work if you're solving this numerically. And those steps are basically, number one, define a coordinate system. Is it Cartesian? Is it cylindrical? Is it spherical? Define a coordinate system. And when you define a coordinate system, you also must determine where the origin is, right? Figure out where your origin is. That's part of your coordinate system. Number two is write down the vector r and r prime in that coordinate system. And again, this may vary as a function of your surface or along your line. Number three is whatever you have determined in number two, your expression for r prime and r, substitute that into the integral. right? So substitute these results into the integral. All right, number 4 is based on your coordinate system, you want to substitute your dl, your ds, or your dv accordingly, largely depending on which coordinate system you selected. And if you're integrating over a surface, what type of surface is it? Is it a surface that's kind of along the shell of a cylinder, or is it a slice that's inside a cylinder? Number 5, you got to set the limits accordingly to capture the entire space over which your charge exists. So this is going to capture the charge. And then you want to simplify it as much as you can. All right. So when you do this in reality, you may end up with something that you can't actually solve analytically, right? So if I tell you that, the integral of sine, right? You know the answer to that. You know the integral of sine is it's a negative cosine. But if I give you something weird, if I give you some much more arbitrary expression that's much more complicated, very often there is no analytical answer to what the integral is. But you can always figure out what an integral is sort of numerically, right? If I give you this arbitrary function and there's no equation for it, but I can tell you what number is anywhere. Maybe there's a big lookup table, right? I have a chart right here. Let's say this is x, right? And this is x, and this is this function of x, right? Maybe this is 0, 1, 2, 3. And you know the values of x of f of x everywhere. It's 1, and then it's 3, and then it's 2, and then it's 5. From that, you can basically imagine dividing this up into little pieces and summing up the contributions of each of these pieces. So this piece we're going to approximate as being constant over this delta x, right? And then we have a new constant value here over this delta x. And we're just going to sum up those discrete contributions to get the total integral, or the area underneath this entire curve, right? Which is an integral. So that's the way real world problems are done numerically. And we're going to see a little more of that later, but I just want to kind of lay down that concept now, that in the real world, problems like this are solved analytically because, again, there are a very small number of problems for which there exists a straightforward analytical answer. However, if you do want to see an example of an analytical answer, there is one in the notes. It is a thicker disk of charge. It has a thickness to it. So it's somewhere in between the ring of charge and the disk of charge. In the notes, you'll see analytically how you might go about solving that. So that concludes this lecture FNW4 on electric fields and charges. We'll move on next and start to do a little bit more and describe other things that result from these charge and electric field configurations.